Hello everyone and welcome to the video on Riemann sums and definite integrals. Our objectives for this one are number one, understand the definition of a Riemann sum. Number two, evaluate a definite integral using limits. And number three, evaluate a definite integral using properties of definite integrals. Now in number two, you evaluate a definite integral using limits. That's going to be very similar to what we did in 4.2. So I won't necessarily do any particular problem with that, but a lot of what we'll be working with in this video is going to deal with what a Riemann sum is and using the properties of definite integrals to evaluate those integrals. I apologize right now for the pen that I've been using. It's not working as well sometimes, but I have what I get on this one. And what we're going to look at here is the definition of a Riemann sum. So we're going to let f of x, be defined on a closed interval from a to b. So that is the interval from a to b. And we're going to let this capital delta be a partition of that interval from a to b. Now what that means is we're going to break up the interval from a to b into pieces. Now in 4.2 we restricted that to be a regular partition where the distance between each point was the same. In this case that is not going to be the case. We're not going to set it up so that the delta x's are always going to be the same. And this partition is going to be given by a equal to x0. And that's going to be less than x1, which is less than x2, which is less than blah, 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 all the way down to less than x sub n minus 1, less than x sub n, which equals b. Now, what we're going to have is the delta x sub i's is going to be the width of the ith subinterval. So the distance when I look between any two consecutive x values from here, that's going to give me a delta x sub I. Now, what's going to happen is c sub I is going to be a point in the ith subinterval. And then, when I take the sum as I equals 1 to n of f of c sub I times delta x sub I, that is called a Riemann sum for the partition capital delta. Now, you should notice this looks very familiar. This is what we dealt with last time in terms of the area of the rectangle. My delta x sub I is the base of the rectangle. The height of the rectangle is the function's value at our point c sub I that's in that interval. And when I take all those rectangles and add them up, that is going to be an approximation for the area. And when I do that, because we're working with any size rectangles, this is called a Riemann sum. Now, a piece of notation here. When we see this symbol where it looks like the double absolute value signs around the delta. That is the capital delta representing the partition. This is called the norm of the partition. And what that represents is the width of the largest subinterval. In other words, if I take a look at all my delta x sub i's, the largest one is going to be what is called the norm of that partition. Okay, and so what's going to happen here, because we're not looking at a regular partition, we can't look at this as the limit as n goes to infinity. What we're going to be doing is looking at the limit as the norm of my partition goes to 0. As that norm of the partition goes to 0, that means my largest delta x sub I is going to 0. So as that happens, that means that we're getting into an infinite number of rectangles, and so we're able to go through and evaluate that limit, and if the limit exists, that is going to equal L. And that then, because of how we've set this up, this is the height of the rectangle, that's the base of the rectangle, and as this goes to 0, it means n is going to infinity, so we're getting the area between the curve and the x-axis for f of x. Now let's look at what we call a definite integral. If f of x is defined on a closed interval from a to b, and the limit of the Riemann sum over our partition delta is equal to the limit as the norm of delta approaches 0 of the sum as I goes from 1 to n of f of c sub I times delta x sub I. If that limit exists, then we say f of x is integrable on the interval from a to b, and that this limit is equal to this right here. And that is the notation for a definite integral. That is read as the integral from a to b of f of x dx. The integral from a to b of f of x dx is the definite integral of f of x from a to b. And if f is continuous and non-negative, then this definite integral will represent the area between the curve and the x-axis. It's important to remember here that this limit is equal to that definite integral. Now some properties of definite integrals that we're going to be working with. First up, the integral from a to a of f of x dx equals 0. Well, that should make sense because if we're going from a to a, we're not changing anything. So our base, if you will, would be 0, and so the area would be 0 as well. Then the integral from a to b of f of x dx is equal to the opposite of the integral from b to a of f of x dx. Number 3, the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. So in this case right here, when we want to combine these two, if these two are the same, then that is going to represent the integral from a to b. Two other ones that are going to be similar to ones that we dealt with the indefinite integral we talked about before. The integral from a to b of k times f of x dx is going to be k times the integral from a to b of f of x dx. And then when I integrate, do the definite integral from a to b of the sum or difference of two functions, it is going to be the sum or difference of the definite integral of each one of those two functions. So those are our properties that we're going to be dealing with here. Now, as you're working with these things, please be aware of the limits of integration because that will come into play. Usually when we look at this, we have the bottom one is the lower limit of integration, the upper one is the upper limit of integration. And in general, most of the time the smaller value is going to be in the bottom and the larger one will be on the top. But there will be times like this where we do switch those. And so you got to keep that in mind and be aware of what that means in terms of evaluating that particular definite integral. Now let's take a look at a couple examples. In this first example, you're going to see some problems like this in the book. We're going to tell you that the integral from a to b of x cubed dx is equal to 20. And the integral from a to b of dx equals 7. So what we want to do is we want to find the integral from a to b of 5 minus 2x cubed dx. So what I'm going to do now is I'm going to use those properties of definite integrals to break this up. Very similar to some of the things that we did in terms of the summation stuff just in the last section. So I have the integral from a to b of 5 minus 2x cubed dx. Now by that sum and difference property, the fifth one I think it was in the previous slide, that is going to equal the integral from a to b of 5 dx minus the integral from a to b of 2x cubed dx. Now, by the fourth property where we had the constant times a function, I can pull that out. So this is good. This thing here is going to become 5 times the integral from a to b of dx minus 2 times the integral from a to b of x cubed dx. Now here's the part that we have. At this point, I know it's given that this definite integral, the integral from a to b of dx, that is equal to 7. So this will be 5 times 7 minus 2 times this integral, which is told to us up above to be 20. So it's 5 times 7 minus 2 times 20 gives me 35 minus 40, which equals negative 5. So the value of this definite integral is equal to negative 5. Please note in this case too that because of how this is working out that we are not dealing with this one is not giving us the area. Why is that? Well, because at some point in this one, obviously what's happening is that we are dealing with something that is below the x-axis. So when we are below the x-axis, now we're going to be getting into negative values. Remember that when we talked about earlier that it's the area when it is continuous and non-negative. If it goes negative, now all of a sudden the value of the definite integral is not going to be the area because there's going to be portions, the part that is negative, the part that's below the x-axis will end up being taken away. Another thing that they'll do is they'll give you a graph. Now this is my attempt at a graph here. I am told I have that this is made up of 3 line segments. These are supposed to be linear functions. I have one, the first one goes through from the point 0,4 to the point 5,0. So we have that line there. And then we have another one from 5,0 to the point 7,6, and then from the point 7,6 to the point 9,3. So what they're going to ask me to do now is they're going to ask me to identify and evaluate some definite integrals. So in this case, I'll take the integral from 0 to 5 of f of x dx. Well, in that case, what I'm looking at is a triangle. And I happen to know that the area of a triangle is 1/2 the base times the height. So I know my base is 5, my height is 4. So the area of this triangle is going to be 1/2 of 5 times 4, which equals 10. Well, that value then is equal to the definite integral, because the definite integral, since it's positive and continuous here, the definite integral is equal to the area of that triangle. It's equal to the area between the curve and the x-axis, which happens to be that triangle. The next one is the integral from 7 to 9 of f of x dx. Well, when I look from 7 to 9, what I'm dealing with in this case on this one is we're really looking at a trapezoid. Let's pretend I got those straight. I have a trapezoid here. And so I am finding the area of that trapezoid. Well, I have a formula for the area of a trapezoid. I know the area of a trapezoid is 1/2 the height times the sum of the 2 bases. Now you have to keep in mind here that on these problems, my base is actually equal to delta x. So in this case, delta x is 2. The heights are. My bases are these 2 vertical lines that go from the x-axis up to the point 7,6 and the x-axis to the point 9,3. Those are the bases of that trapezoid because they're the 2 sides that are parallel. So in this case, this definite integral, it is positive, it is continuous and non-negative over that interval between these limits of integration. So I know the value of that definite integral is just going to be the area between the function and the x-axis over that interval. And since it's a trapezoid, it's going to be 1/2 times 2 times 6 plus 3, which comes out to equal 9. So this area here is equal to 9. The third one that we have here is the integral from 0 to 7 of f of x dx. Now I put this one in red because it does illustrate the third property that we for definite integrals that we looked at. The idea that we can break that up and write this integral, this is supposed to be from 0 to 7, we can write that as the sum of 2 other definite integrals. And what we're going to do is we look here, we notice that when I go from 0 to 7 here, I have 2 different regions, and one goes from 0 to 5, the other goes from 5 to 7. So I can say the integral from 0 to 7 of f of x dx is equal to the definite integral from 0 to 5 of f of x dx plus the definite integral from 5 to 7 of f of x dx. So what I have to do is just find those 2 areas. Well, I already know this one. We found that up here in number 1, so I know this is equal to 10. The integral from 5 to 7 of f of x dx, well, that's another triangle. And you can see that right here. So that is going to be 1/2 the base, which is 2, times the height, which is 6. So when I take 10 plus the 1/2 times 2 times 6, that comes out to equal 16. So this definite integral is equal to 16. The last one I want to look at is this one up here, which is number 4, right here. And that is the integral from 5 to 0 of f of x dx. Now notice this time the 5 is down below. So in this case, what we have to remember on this one is that, because we usually look at the definite integral from from the lower to the upper, I know that this one right there is by one of our other properties, that is going to equal the opposite of the integral from 0 to 5 of f of x dx. So in this case, again, I know this integral here is equal to 10. So in this case, I know this one here comes out to equal negative 10. So that is our last property, our last example for this particular section. So this does conclude the video that we have for this section. In class, we'll do one more example, I think, in terms of doing the limit process for finding those limits. But we'll really focus on looking at finding these areas and using the definite integral from graphs and from tables and other types of figures. So anyway, with that, I hope you do have a good evening, and we will see you in the next class.